Hey there, so we're continuing with the Chapter 8 practice exam. 1 through 17 is on a different video than this one. So if you want those problems, then you'll need to watch the other video. So we're starting with problem number 18, and we are doing the full shebang here. So as we read through this, a manufacturer considers his production process to be out of control when defects exceed 3%. That means our null hypothesis is going to be P, because it's a percent or proportion, is equal to 3%. Our alternative hypothesis is that when it exceeds 3%. In a random sample of 85 items, so to be clear, that's n equals 85, the defect rate, so our P hat, is 0.059. But the manager claims this is only a sample fluctuation and that production is not really out of control. At the 1% significance level of significance, test the manager's claim. So before we get going on this, we're here. And because it's larger than, this is going to be a right tail test. And they give us an alpha, so 0.01, so this. And let's find the critical value. So that's inverse norm. And remember, critical values are, to use inverse norm, it has to be area to the left, so I have to do my 1 minus 0.01. So our critical value is 2.326. All right, and we need a test statistic. And if you remember, the test statistic, which is on this sheet here, is right here. So for our test statistic, which is our comparison for here, we're going to go Z is equal to P hat minus P over the square root of PQ over N. And we have N and we have P. Q, if you recall, is 1 minus P. So in this case, Q is going to be 0.97. So plugging all this in, 0.059 minus 0.03 over the square root of 0.03, 0.97 over 85. Now, I'm going to show you how to put this in your calculator. This gets a little tricky. I'm going to use parentheses in the numerator. So 0.059 minus 0.03 divided by, now you may need extra parentheses with your calculator. Mine keeps the radical all the way across, so everything's under the radical. You may need to double up on the parentheses to do it depending on how old your calculator is. So I'm going to go 0.03 times 0.97 divided by 85. And notice mine's all under the radical like that. So here's our test statistic. .567, which is not in the critical region. That goes right there. Now we can get a p-value from that. The p-value is going to be normal CDF. The lower in this case is the 1.567. The upper is just any large number. And the p-value is 0.0586, it looks like, which is way bigger than our alpha, which is 0.01. And what that tells us is that we are going to fail to reject the null hypothesis, meaning our test statistic is too close to the mean. This means there is not sufficient evidence to support the claim. What's the claim? Oh, that the proportion is bigger than 3%. I know it's wordy, and we're gonna have to word it that way every time, and I know that can be frustrating, but it is necessary to write out the sentence. That was number 18. Let's do number 19. And I want to point out, just real quick, because they gave us p hat, we had to do the test statistic this way. This next one we can actually use. Let me say that. Because they gave us p hat, we had to use our test statistic by hand. However, when they give us so many out of so many as a proportion, then we can use a program with a calculator. And I'll show you what that looks like. So for number 19, in a clinical study of an allergy drug, 108 out of 202 subjects reported experiencing significant relief from their symptoms. At the 0.01 significance level, test the claim that more than half of all those using the drug experience relief. So let's set up our null first, null hypothesis. And this is a proportion again. And half is 0.5. So more than half is p is bigger than 0.5. And you can see right away that what we have is a right tail. Which means our alpha, which in this case is a 0.01. And to find that, we're going to do inverse norm. Remember, it's area to the left, so I have to do the 1 minus trick. So this is 2.326. Now for the test statistic. Now, I could do the formula that we used before, but let's keep it simple. Because they give us, instead of a percent like they did before, we can run stat tests. This is a 1 proportion z-test. 1 prop z-test. P naught in this case is 50%, it's already there, 0.5. Now, if we look at the problem, x in this case is the 108. That's the numerator. The denominator is 202. And in this case, it's larger than. And it's a work of art, it's beautiful. Look at that, right away, it tells us what our test statistic is. And our p-value. And if you remember on some of the previous ones, we were looking for the p-value, we had to double it sometimes. We don't have to worry about that when we run this. The calculator doubles it if it needs to be doubled and doesn't when it doesn't. So we can just use the value that they give us here. 0.1623, which, to be clear, is way bigger than our alpha. And we can see our Z value is way over here, 0.985. And there's our P value there. The point is, we are definitely failing to reject. Our null hypothesis. So there is not sufficient evidence to support the claim that more than half experienced relief. That was 19. All they're looking for 20 and 21 are the p-value. So that's all we're going to find. We're not going to do a full-on test for those. And let me So 20 says a medical school claims that more than 28% of its students plan to go into general practice. And among a random sample of 130 of the school's students, 32% of them plan to go into general practice. Find a p-value for a test of the school's claim. All right, so we are going to set this up as though we were going to do it. P is equal to 0.28. Says more than. You'll notice they give us a percent again, so we're going to have to find the test statistic. But to be clear, we don't have a critical region in this case. We do not. That's okay. Point is, it's a right tail test. We don't have an alpha, and we don't need an alpha, actually. We just need to know that this is a right tail test. So for our test statistic, we have P, which is 0.28. We have Q, which is 1 minus P. 0.28, 0.72. And we have N, which is 130. And we have P hat, which is the 32%. So for our Z, P hat minus P, we don't have the X and N again, so we have to do it this way. Uh, 0.28 and 0.72 over 130. So again, I'm going to use my parentheses, 0.32 minus 0.28 divided by the square root. 0.28. Again, be careful. You might have to use some extra parentheses as you're setting this up. times 0.72 divided by 130. Mine are all under the radical there. So that's my test statistic. So to find the p-value, wherever that is on the scale, we know that it's right tail, so I'm going to use the p-value is going to be 1.0157 is going to be my lower bound, and my upper bound is going to be the 99999. So here we go. Good. Lowers 1.0157. Upper is 99999. My p-value. Since it's one tail, I don't have to double it. And let's squeeze 21 in down below here. All right, 21. In a sample of 47 adults selected randomly from one town, it is found that 9 of them have been exposed to a particular strain of the flu. Ugh. As we're in a pandemic. Find the p-value for the test for a test of the claim that the proportion of all adults in the town have been exposed to this strain. So we're looking for just the p-value. Now this one's going to be similar, except in this case, the proportion for all adults, yeah. So p is equal to 0.08. And the claim is that it's not 0.08. Yes. All right. So we are going to have to be clear, this one very nicely, they gave us the X, so we can run the little testing. We don't have to do it manually like we did here. Was 9. N was 47. And yeah, I think that's all we need. So let's go back to here. And we're going to go to stat and tests. Again, this is a 1 proportion z-test. And p is 0.08. X is 9. N is 47. And this is a not equal to situation. Now, if we had to do this by hand and we got our p-value, we'd have to double that because it'd be 2-tail. But because we're running the program here, that is the actual p-value. So for this one, you run a 1 prop z-test. And we got that the p-value is 0.0048, very small p-value in this case. All right, moving on to number 21. Oh, we just did 21, sorry, number 22. So we're going to do the whole thing with this. This is with a mean now instead of a proportion. A manufacturer makes ball bearings that are supposed to have a mean weight of 30 grams. A retailer suspects that the mean weight is actually less than 30 grams. The mean weight for a random sample of 16 ball bearings is 28.6 grams with a standard deviation of 4.4 grams. At the 0.05 significance level, test the claim that the sample comes from a population with a mean weight less than 30 grams. And even when it says use the traditional method, you can use the p-value or the traditional. I'm going to tend to use more the p-value. All right. So I want to point out that we are dealing with the mean in this case. And this is a less than 30 grams. Remember, the null is always equals. All right, and I'd like to point out they give us no information at all about the standard deviation of the population. They do give us the standard deviation. So they do give us, let's write down, so n is 16. X bar, this is the mean of the sample, is 28.6. And our sample standard deviation, which is an S, not a sigma, is 4.4. And let's set up, oh, and our alpha in this case, there, 0.05. So let's set up our picture here. And this is left-tailed because it's less than. And let's find our critical value. Inverse norm. Distribution, inverse norm. Remember, this is area to the left, so it's just the 0.05. I don't have to do my 1 minus trick. And here is our critical value. Negative 1.64, we'll say. All right, now to the test statistic. Now, to be clear, this is a one sample t-test. Which with the t, I forgot to just call it a t-test. And you can see we're going to use our stats. So we have mu is 30, x bar is 28.6. Standard deviation is 4.4. This is, again, the sample standard deviation, not the population standard deviation. And this is a, n is 16. Yeah. And then this one is a less than scenario. And here we go. Negative 1.27. So t in this case is negative 1.27. And our p-value is about 0.1112, which is definitely bigger than alpha, which is 0.05. So that means we are back here. So our 1.27 is right there. And we're clearly not in the critical region. So let's come to a conclusion. So fail to reject the null hypothesis. So there is not sufficient evidence to support the claim that the mean weight is less than 30 grams. Cool stuff. Number 23. Now, this one's going to be the same in the sense of it's going to be a t-test and all that. How are we doing on the camera there? Okay. All right. In tests of computer component, it is found that the mean time between failures is 520 hours. A modification is made, which is supposed to increase the time between failures. Tests on a random sample of 10 modified components result in the following times and hours between failures. At the 0.05 significance level, test the claim that the modified components, the mean time between failures is greater than 520. So let's set up our null hypothesis. Is bigger than 520. So here we're going to have a right tail. And let's set this up. Alpha is 0.05 in this case. And it is a right tail test. So here's our critical region. In this area here is 0.05. And to find that critical value, I'm going to do inverse norm. Remember, it's area to the left, so it's going to be 1 minus 0.05. Making our critical value a positive 1.64, and you can see that that's the positive version of that. All right, test statistic. Now for this one, this is also a t-test. But instead of having the statistics, we have raw data. Now, I have already put into my list one these values, 518, 548, and so on. So you may need to pause the video and put those into your list, list 1, 2, 3, wherever you want to put it. But I'm going to move on. This is a t-test. We're going to use the data. And here, we're going to go 520. I put mine in list 1. Remember, to find the lists, you need to 1, 2, 3, 4. Here's the 6 major lists. And make sure you hit the blue button first, or whatever color your button is. And frequency is just 1. And this is a greater than scenario. So this gives us that T is 2.612 with a p-value of 0.014, which is definitely less than our alpha. So that means we are here. So we are definitely in the critical region, which means reject the null hypothesis. There is sufficient evidence to support a claim that time between failures failures is more than 520. These are hours. Here's our 23. All right, so number 24. All right, so 24. Various temperature measurements are recorded at different times for a particular city. The mean of 20 degrees Celsius is obtained for 60 temperatures on 60 different days. Assuming I've noticed in this case, they make a big deal. They have the sigma. They have the population standard deviation is 1.5 degrees Celsius. Test the claim that the population mean is 22 degrees Celsius. And I'm going to actually modify this a little bit. I'm going to say test the claim that the population mean is not 22 degrees Celsius. So I'm going to change it slightly than the way the book is. You can do that on all the test questions. So the mean, 22. And again, I'm modifying this slightly. And this is going to be a z-test. I want to set up, this is a z-test. Oh, I should write here, this is a t-test. This is z-test. And we are given n is 60. X bar is 20. And sigma, the known population standard deviation is 1.5. Let's set up our regions here. All right, this is a two-tail. Alpha is 0.05, so this is going to be half that, 0.025. And I'm only going to get one of them because the other one's going to be the positive version of that. So this is going to be inverse norm. 0.025. This will give me the negative one here. Area to the left. Negative 1.96, making this positive 1.96. All right, so let's run our z-test. So stat tests z-test. We actually have the statistics. We don't have raw data. So mu in this case is 22. The known standard deviation is 1.5. Population standard deviation, the mean is 20. N is 60. And this is a not equal to scenario. Ooh, okay. Now, to be clear, your p-value, the numbers may be slightly different. Depending how old your calculator is, it's not good at calculating. This is actually a tiny number. This is 5.38 times 10 to the negative 25th power. So when I write down the p-value, I'm going to put 0 because it's so close to 0. So for a test statistic, z is negative 10.33. which means our p-value is about 0. And you can put that on the test, 0. So what's our conclusion? That means we are way over here. So we're going to reject the null hypothesis. So there is sufficient evidence to support the claim that the temperatures have a mean not 22 degrees Celsius. Remember, I told you to change it to not. All right. We have 4 more problems to go. Number 25. Let me fix the camera here. And you will need this table available. You'll need it for the test for sure. So make sure that you get the chi-square distribution table. You can print it out from the MyMathLab website, or if you just type in chi-squared table, there's millions of them. I mean, you won't have any trouble getting a hit. All right, number 25. The null hypothesis implies that sigma is 9.3 because the alternative hypothesis they tell us is that sigma is not 9.3. This is going to be a two-tail test. They give us that n is 28, which means our degrees of freedom is 27, and alpha is 0.05. Let's draw this. Remember, chi-squared graph is skewed right. This is a two-tail. So this is chi-squared right, and that has 0.025. We have to cut that in half. Here's the other half. This is going to be chi-squared left. All right, so to be clear, our chi-squared table is assuming that this top part is the area to the right. So if alpha is 0.05, that means this middle part here is 0.95. So to get the area to the right here, I add those up. 0.95 plus 0.025. 0.95 plus 0.025 gives me 0.975. So I'm going to go here. Degrees of freedom is 7. How are we doing on 27, which is way down here. Can we see that? We can see that. So here's 27. And area to the right is the 0.975. So where do those two meet? We were here at 14.573. Degrees of freedom of 27. Area to the right is 0.975. 14.573. Here, the area to the right is the 0.025. So degrees of freedom are the same. I'm still down here at 27, but now I'm up here. So 43.194. 43.194. Double check my numbers. 14.573, yes. And 43.194, yes. So there are the critical values. And that's all they're looking for with 25. Moving on to 26. All right. 26 says that we have a null hypothesis of sigma equals 3.5 versus sigma is bigger than 3.5. They give us that n is 14, which means our degrees of freedom is 13, and an alpha of 0.05. I'm going to over-exaggerate that one a little bit. Now this is going to be a right tail because it's larger than. And so there's only going to be one critical value in this case. So area to the right is going to be 0.05. 0.05. Degrees of freedom in this case are 13. So 13.05. We are right here. Looks like 22.362. So that's my one critical value for this one. All right, we got 2 more tests to do, then we're done. You can see why I split this one into 2 different videos. All right, let's get that up. 27. All right, so here we go. The standard deviation of math scores at one high school is 16.1. A teacher claims that the standard deviation of the girls' test scores is smaller than 16.1. A random sample of 22 girls results in scores with a standard deviation of 12.9. Use the significance level of 0.01 to test the teacher's claim. All right, here we go. So it says to test the scores are less than, the standard deviation is less than that there. And they give us that n is 22, which means our degrees of freedom is 21. They give us an alpha of 0.01. This is going to be a left tail test only. I should write out the rest of that. So they also give us that the sample standard deviation is 12.9. And n we already have, alpha we already have, all right. So this is a left tail test. And this is going to be 0.01, which makes all of this 0.99, area to the right. So degrees of freedom is 21. And our area to the right is 0.99, so 21 is here, 0.99 is here. So my critical value is 8.897. 8.897. And we're going to find our test statistic. Now, we don't have a fancy button for this one, so we have to use the formula. And the formula is right here for our test statistic. So for our test statistic, we're going to have to calculate this. So chi-squared is equal to n-1 sample standard deviation squared over the population standard deviation squared. So n-1 is here, 21 times 12.9 squared over 16.1 squared. So 21 times 12.9 squared divided by 16.1 squared. And we can see, don't forget this starts at 0, 13.48 is right there. So we are not in the critical region. We could do p-value, but I don't want to confuse with it. So this is so not in the critical region. So the test statistic is not in the critical region. So fail to reject. The null hypothesis. So there is not sufficient evidence to support the claim that the girls' standard deviation is less than 16.1. Whew, my hand's cramping. All right, we got one more to go. Number 28. Now for number 28, as you're looking at it, you see raw data, and I have already put that data into list 2. Oops. There's the 115 and so on. So you may need to pause this video and put that in. I'm just going to go ahead and push forward. 28, this is it. For randomly selected adults, IQ scores are normally distributed with a standard deviation of 15. The scores of 14 randomly selected college students are listed below. Use a 0.1 significance level to test the claim that the standard deviation of IQ scores of college students is less than 15. Round the sample standard deviation to 3 decimal places. There's a lot going on there. Let's start with our null hypothesis. So the claim is that it's less than 15. They give us n, which is 14, which means our degrees of freedom is 13. They give us, yes, okay, so they give us the raw data. And what I'm going to do with that raw data is I have to get, if you remember the formula, has the sample standard deviation and the population standard deviation. I have the population standard deviation here. However, what I'm going to do is I'm going to run one variable statistics on list 2. Now, I want to make sure we remember how to do that. List 2 is above 2 here. It's in blue on mine, so I hit second in list 2. There is no frequency list. I want to clear that. And then calculate. And here's the value. Now, you'll notice on the problem, it specifically says round the sample standard deviation to 3 decimal places. So S in this case, we're going to round to 3 decimal places. That's here, 9.819. All right, so let's set up our nifty graph here. So once again, this is a less than scenario. And the alpha they gave us is 0.1. That's quite large. So we're going to find our critical value. Our degrees of freedom are 13. Area to the right is 0.9. So degree of freedom of 13. Degrees of freedom of 13 is here. Area to the right is 0.9, we're here. So our critical value is 7.042. 7.042. And now it's time for the test statistic. Once again, the formula is here. So we have 13 times 9.819 squared divided by 15 squared. Ooh, that puts us in the critical region. The test statistic is in the critical region. What does that tell us? Reject the null hypothesis. There is sufficient evidence to support the claim. That, I already forgot what we were talking about. These are IQ scores. that the standard deviation of IQ scores is less than 15. So there you have it. I hope you found this helpful. Good luck on your test.